All right, welcome back. We are Game 2005 in the fall 2021 semester at George Brown. It's Game Physics, and it's week 3, part 1 of our broadcast. Let's see where we are right now and what's happened so far. So last week we talked about motion in one direction. I also released assignment number 1, which is due next week on Friday or Sunday. I can't remember which day that is. We'll take a look at that later. This week we're talking about motion in two directions, and again we're moving into the laws of motion next week and so on as we spin towards the mid-semester test and the mid-semester break. So that's what's happening right now. Let's just do a little bit of administration. Right now, from an assignment groups perspective, there are many groups. As you can see, there's a couple of groups that are empty. So again, assignment groups 3, that is an empty group. Some people are asking to create groups. There's assignment groups 25, that's also empty, 27. And there are people also that may have joined some groups that are that want to leave. You can't leave on your own. That's the negative thing about Blackboard. The only person that can get you to leave is me. So if you want to leave a group and you want to join another group as an example, or just do it on your own, please let me know, and so I can remove you from a group that you're in right now. Okay, so that's kind of the first thing. You can't do the assignment. So let's take a look at that assignment again from last week. You can't do this assignment. You can't even see the assignment to submit until you have signed up for a group. So you must do that if you haven't done it already. And there are still quite a few of you who are not participating in that group assignment. And I'm just going to call some of those people out just to make sure that we're good to go. Let me just make sure that we have everything in play. So let's see. So we have, quite a few people here. So Pedro, I'm seeing that Ethan's not participating so far. Christina, we're looking at Alexander Bellato. These are all the people that do not have a group or have not joined one. Evan, Michael Ferrazzo, we're looking at Andre. So quite a few of you still don't have a group. Brandon, and we've got Austin, and I'm sorry to call you out like this, guys, but it's going to make you crazy coming up. Shafkat, we've got Rico. We also have McKinnon. Again, all these people haven't had a chance to join, or maybe just haven't joined yet. Micah, and that means you may have not started your assignment as well. And Eric, those are the people that haven't joined right now. If you need, obviously, for all those people, I'm going to need to make additional groups. So that's okay. I will create them for you. But in order for you to do that, there are a couple groups here that are empty that you could certainly just join, and at least 3 groups that I'm seeing that are not used that you can connect with and be good. Okay. If I look at group sets, I've made a bunch of them, right? So I've made a bunch of group sets already. So A1 groups is what I've called it, and I keep on making new ones as an example. If you need a group, please see me at the end of class as an example. If you haven't, then you won't be able to do your assignment, and that would be pretty much catastrophic for you from a grade perspective. All right, so please, let's not do that. I highly recommend that you get that sorted out as soon as possible. Otherwise, it's going to come back and really affect you in your performance, right? So please don't do that. That would be bad. Okay. So we're sitting at week 3, and I want to start talking about motion in 2 directions. Let's move on from there. So welcome everyone, for the people that have joined. Hopefully, you've started your assignment at this point. There are 2 portions of it, like we talked about last time. One portion is kind of the theoretical piece, and the other portion that you're going to see is a technical piece where you're going to have to build out your physics simulation based on the theoretical piece that you're doing. All right, so motion in 2 dimensions. Let's talk about that a little bit. So far, last week, we talked about motion in 1 direction, and we said that there's a difference between distance and displacement. Can anyone remember what the difference between distance and displacement is before we get over these definitions here? Distance and displacement, what's the difference? Maybe on a test. Hint, hint. Sophia says distance is scalar, displacement is a vector. Yeah, that's definitely true. But if you were going to explain it, Sophia, what does that mean? Right? So does it mean, how would you put it down into words for, common words for a user to understand? Vitaly says vector has a direction, right? Okay, that's fine. But there's more when it comes to displacement, right? Neil says, is it okay if the projectile starts and ends at the same height? Or does it have to start from the Wookiee's hand? Okay, this is an assignment question, and land on the ground. It starts from the Wookiee's hand. Displacement is the distance from the original start point. So if you go back to the starting point, the displacement is 0. Yeah, distance is greater than or equal to 0. So yeah, so exactly right. So the way it works is this: when you have displacement, you have an origin, right? Some kind of origin or origin point that you start off with. And what you're measuring from that reference point is the amount of the distance that you're traveling away from the reference point, whether it's a positive distance away or a negative distance away. It's still some kind of measurement, a length, a magnitude, if you will, that is away from the origin, okay? So whereas distance, like Nihar says, is the total amount traveled, and you add it up, you don't care about, the displacement from a reference point, like the origin. What you're caring about is the total amount traveled altogether. So let's think about some other things here for today. Speed, distance traveled per unit time, all right? So distance over time. Velocity, the object's speed and direction of motion. So we have acceleration, which is the change in velocity over a period of time, and gravity, which tends to pull objects towards the center of the Earth or the center of mass of a larger object like a planet or a moon. That's no moon. Gravitational acceleration, a constant that describes the acceleration of any object falling towards the Earth, and that is for us, for our points, for all intents, 9.8 meters per second squared. Some people in games also do things like 10 meters per second squared because it's close enough, right? Although I'll tell you that if you make a platformer and you do 10 meters per second squared, you're going to see that that is a little floaty when it comes to how it looks in a game. You might want to do something like 3 times that amount, like 30 meters per second squared when it comes to jumping and falling, because it'll be more exciting. All right, let's think about kinematics in 2 dimensions now. So we've talked about kinematics in 1 dimension, and now we have 2 components of motion. We don't just have one. The first component is on the x dimension, the x-axis, and the other component is on the y-axis. Notice how on the y-axis, the time steps become longer and longer when I drop an object, a projectile. So this is a projectile motion. Notice how this is. So it comes longer and longer. In other words, it goes faster and faster. It accelerates. But along the x-axis, that the time step is the exact same. Okay? Why is that? Because gravity does not affect an object along the x-axis. It affects an object only on the y-axis. The total effect across both axes gives you a parabolic motion, but only the y component is being affected in terms of acceleration. So this is acceleration across the y-axis, not across the x-axis. Okay. So we thought about this, the idea of position and displacement. We've talked about that. And again, sometimes we talk about this little mark on the top. It also is a vector, where the final position, r being the position or displacement, minus the initial position is equal to the change in position over time. right? So this is the displacement vector from A to B as an example, the change in position, right? Or displacement, if you will. So something that we're going to see a lot is vectors. We're going to see vectors pretty much everywhere, right? So let's think about some general motion ideas. So again, in 2 or 3-dimensional kinematics, everything is mostly the same as what we've seen already in 1 dimension. What we're doing now is we're seeing we need to use full vector notation a lot of times. Positive and negative signs aren't enough a lot of times to tell us information about the direction. We have to have the vector for the velocity and so on for x and y. When we talk about the average velocity now on 2 dimensions, again, we're looking at the same kind of equation we saw last day, which was the change in displacement over the change in time is the average velocity. And when we say the change in displacement, the displacement being a vector, it's not distance, right? And the vector is actually a 2-dimensional vector with, again, which gives us, in this case, we're only thinking about 2 dimensions. We're not looking at 3 dimensions necessarily. It's going to give us both direction and magnitude. All right, so that's kind of the important things there. Okay, so same equation, but we have to keep in mind now that the vector that we're using on the top for displacement has x and y components. We also looked at instantaneous velocity. This hasn't really changed, but we're thinking about the kind of a line that is tangential to the curve. So if we have a curve of motion, the line that's tangential to the curve or at right angles, the point that it touches the curve is, we can say that is the instantaneous velocity at that point in time, okay? And you can see that if you keep going with that curve, the line is going to change direction as you move around the curve, right? So again, when we think about instantaneous velocity at any point in time at a part of a particle's path, what we're thinking about is we're using, a lot of times we use calculus to calculate that, and it's usually velocity. Instantaneous velocity can be derived from the position formula. So if I have a position formula, and as an example, we can derive velocity from position. We can derive acceleration from velocity. And we've seen that kind of relationship last week. Okay. So again, average acceleration. And again, think about these little marks as just the same as an arrow. These are just little marks that the book used, right? But at the end of the day, it's your V final minus V initial. So velocity final minus velocity initial over time final minus time initial. A lot of times we say time initial is 0, which means it's just the total time that we're talking about here. So it's delta V, it's delta velocity, change in velocity over delta time, delta T, right? Gives you your average velocity or your average acceleration with respect to distance, okay? So again, when it comes to average acceleration, the particle moves in the direction, as an example, and you can see that as the direction changes. As an example, we can calculate the acceleration, around kind of the curve, and we can figure out the formula based on the directional changes of the particle. A lot of times, the particle is changing direction because you have some kind of forward motion, but you also have a downward motion due to gravity. A lot of the things we're going to be talking about is going to be affected by gravity. Again, the instantaneous acceleration is very similar. We want to find on the acceleration graph a tangent to that graph as the limit approaches 0, time approaches 0, from the change in velocity. The rate of change, we say, of velocity over the rate of change of time. Usually rate of change is what we're looking at. We can get the derivative of the velocity to get the acceleration. So the first derivative, or velocity prime. So again, one thing we need to do to produce an acceleration is the magnitude of the velocity vector has to change. All right, so we want it to change over time. If the velocity vector stays the exact same, the magnitude of the velocity vector, this means that there's no acceleration, because the size of your vector, the size of that arrow, stays the same for every time step, right? Direction also may change, and that's because you might have forces, and we'll talk about forces starting next week, that push a particle in a particular direction, because again, we're going to break those forces down into these two dimensions, the x component and the y component, which is what we've talked about from the kind of the very beginning. So when we looked at kinematic equations for 1 dimensions, the kinematic equations for 2 dimensions are very similar. But we have to respect both the x and y axis now, not just the x axis or the y axis, not a single axis formula anymore. So what we can do is we can break down the components of x and y, and we can kind of say something like the I and the j with the little hat on top of it is kind of the component with respect to the x-axis with respect to the y-axis. That's what this notation usually means, right? The x component, and here's the y component. The x term and the y term creates the total vector. So we add those two things together as an example with a vector for a particle moving in the xy plane, and this is the equation that we normally get. And a lot of times when we want to think about a vector, we have a vector initial across the x-axis and a vector across the y-axis. We add those two vectors together, and then we get the total vector, right? So we do vector addition, and we'll talk about how that might look. So let's say if we were to draw that out as an example, and just use the annotate tools to help me out here. So if I'm drawing out a vector in this case, and I have a vector kind of across the y-axis, this is my vector across the y-axis, and if I have then, and it's tip to tail, typically what we do, right, that's how we do. So there's my arrow. So this is the vector across the x-axis. And then I draw I kind of add them up. I take the vector across the y-axis, let's say up this way, and I draw that one. Okay, so, and I'm going to draw it not just with direction across the y-axis, sorry, it's not exactly perfect, but also magnitude. Notice the magnitude here is the length of the vector, and here's another length of vector. And then what we're going to do is we're going to take these two things, and I'm going to take it from the starting point of the first vector and draw it to the ending point or the arrow of the second vector to give me my total direction. So this is the total vector, all right, that we have here. And what does it look like? A triangle. And this is why we started off with triangles in the first place, because we want to take the x component as an example. So let's go back to our annotation for a second. So what we do is we take the x component here, right? So here's our x component. And we take our y component, and then what we do is this y component isn't just, it's a vector. So we have the x vector and the y vector. We add those two vectors up. So the x component vector and the y component vector, two different directions, right? Usually they're just right across the y-axis. So that's why it's xi, yj, right? And then zk, ijk, right? It basically describes a vector quantity across. So where the y or the x and y are the magnitude, and the I and j and k, as an example, if I was going to do the three-dimensional vector, would be the vector. So I take the magnitude of what I'm drawing here across the x-axis or across the y-axis, and I multiply it by a scalar to get the magnitude that I'm looking at here. It's always across the axis with respect to the axis, okay? So that's how it works. So then x and y, and then I get the resultant vector, whatever this is. Okay, this is the hypotenuse typically. Make sense? So again, I'm showing you this because one of the confusing parts when we look at two-dimensional or motion in 2 dimensions is like, how does this all work, right? And it's pretty simple actually. But we got to talk about this is because we're going to be decomposing a vector or kind of decoupling the x and y component vectors, and then we're going to do things with them to solve problems going forward. All right. If I can also get you guys, the people that have joined my Zoom session, if I can get you please to rename yourself so your name reflects what I see up on Blackboard, please. All right, so so again, that was kinematic equation number 2. Kinematic equation number 2 was, just like we saw before, v final. So the final, vector is equal to the initial vector of velocity. So final velocity is equal to initial velocity plus acceleration multiplied by time, which you've seen before. But now these vector quantities include are kind of a aggregate of both the x and y vectors, all right, across those axes. Okay, position vector, also very important. We start off with position final, and we've seen this before, this equation, many, many times, right? We saw it before. It can be rewritten in different ways, but we can say that the final vector is equal to the initial vector. So final position is equal to initial position plus initial velocity times time plus 1/2 at squared. Okay, so this is kind of, we've seen this before. This is the parabolic function that we see. If I'm going to throw an object in 2 dimensions, right? As an example, I may be using this formula. So for the Wookiee question, right? It's a parabolic arc. A lot of times what I'm going to be doing is I'm going to put in the total time it takes. I want to try and maybe I've asked you, how long does it take for the Wookiee, the Wookiee's thermal detonator to land on the stormtroopers, right? Kind of thing. And you can figure that out by using the quadratic formula and getting that out, right? One thing to note is velocity initial. This velocity initial, remember, is 2 components. I have energy. I want you always to think about velocity as energy. And I have energy across 2 axes, right? And when we decompose velocity, right, because usually velocity also has an angle, right? Then remember what I talked about in the first lesson, the first lesson ever. I said that think about always, for the most part, that cosine is aligned with the x-axis and sine is aligned with the y-axis. So it's an easy way to think about things. So if I want to decompose velocity, I'm going to take my velocity, multiply it by cos theta, whatever the angle is of my, the direction of my initial vector, right? Based on the x and y components that I'm given. And I'm going to take the, so for example, let's say I say my velocity times time, when my velocity is, let's say 20 meters per second. So there's the magnitude, right? At an angle of 30 degrees. How do I find the x and y components? We're going to see that we're going to take the velocity cos theta for the x component and the velocity sine theta for the y component, and that's how we're going to break those 2 vector quantities down in order for us to understand how far something moves across the x component, how high something goes, before it starts making a downward trajectory. And we're also going to do the same thing for acceleration. But remember that there's no acceleration typically due to gravity across the x-axis. It's only across the y-axis. So think about AY all the time, or gravity. We can replace a lot of times A with G, right? When we do our equations here. So again, I just talked about this, where we can take the components of the initial velocity. So this is something where we can, this is representation of the final velocity, right? Where, let's read this together. We have our initial velocity plus some kind of acceleration over time, and then we're going to get the final velocity. It makes sense, right? And notice that we can break it down into both the acceleration across the y. In this case, acceleration does have a y component, right? Because we have an acceleration factor. So this is the y component from the initial position where velocity, where we start accelerating. We start accelerating about right here, right, as an example. And we measure the magnitude of the acceleration here multiplied by time. So some kind of magnitude only across the y-axis, right? And then we do the same thing for the acceleration across the x-axis. Notice that the x component is smaller because it goes from here. It's measured from here to here, as an example, compared to the y component for the acceleration alone, which is from here to here. Similarly, when we talk about the velocity, the initial velocity that we've been given, we measure it on both components. So the component that starts from the origin and goes across the x-axis, and the component that goes from the origin and goes across the y-axis. When you add those 2 things up, you get this final line over here, and you can see that the y final, right? And the y on the y-axis, and the velocity final or across the x-axis is this. And this this and this adds up to make this big line right here. It's all related, if you will. Okay, so that's how it works. And again, we add things tip to tail. So here is the representation of the final position. Okay, just like the position graph that we had before. We have the initial position, right? So again, the initial position is a vector. The initial displacement, which is what this is. R stands for displacement. So we can see that the initial displacement is not at the origin. It was actually away from the origin some distance when we look at this graph, right? So some amount of x, some amount of y gives us the total, the final or the initial displacement from the origin. This is where we start. Then we add, remember, just like that formula, final position is equal to initial position plus velocity initial times 1/2 at squared. We add all these things together to get the final position at the end. That's how it works. Okay, the final displacement. And this is based on over time. Okay, so again, initial position, if you will, away from the origin or displacement, plus the velocity initial, times time. Again, you can see the velocity component right there. And then plus 1/2 at squared. In this case, we've got a positive acceleration across the x-axis and a much more positive acceleration across the y-axis. And we add all these three vectors together to get the final displacement vector at the end of that time frame, whatever that time t is. Okay? Does this make sense? So we're adding vectors together to get the final things. And you can see that these are the two representations, the graphical representation of those two formula that I just showed you, formula for the kinematic equation number 2 and 3. So when it comes to projectile motions, now we move in both the x and in the y directions. One thing that we're going to be talking about is called projectile motion. So that's the form of 2D motion we care about. Okay, projectile motion. Remember, the projectile is just a point. And so what is a projectile? It's an object that is projected. That's what it's called, or sent, as an example, or transmitted. Sometimes people use that word as well, by some means, and continues to move through its own inertia. Now notice that word inertia. We're going to talk about that later on. Inertia is another fancy way of saying mass, right, in some ways. So own inertia, and the only active force on a projectile is gravity. And projectiles come in many, many types. For example, even a bullet has this trajectory. It's just that it's so fast, the initial muzzle velocity of a bullet is so fast, right, that it's going to drop down much farther on. It's still going to drop over time. Neil says, do we have to use GLM Vec2 for the assignment, or is it okay to separate the x and y in their own floats? I recommend using GLM Vec2. Okay, so let's continue. Although you could, Neil, if you wanted to initially start with floating points and then compose your Vec2 later, it's up to you. So the free fall acceleration constant over the range of motion is something we need to know is it's in a downward direction, right? We mentioned that that's the way it is, right? And the reason why it's in a downward motion is because we don't have negative gravity. We don't have anti-gravity or something weird. All of our gravity, when it comes to projectiles on Earth, they're all towards the Earth. That means they all fall, every projectile we have falls towards the Earth. If it's not a projectile, and if it's powered in some ways, that's a different scenario, okay? One thing we also want to think about is that the effect of air friction is negligible for our examples as before, right? So that's one thing to note. And with these assumptions, all projectiles should follow a parabolic path. That's that, that path that is generated by P final is equal to P initial plus V initial times T plus 1/2 at squared. That formula is the parabolic formula that you need to know, all right? And this path is called the trajectory. And whenever I hear trajectory, it's a fancy word. I'm like, my trajectory when I'm flying. It's a trajectory, and it's the kind of the path that the projector will take. It's usually a parabolic path over time. Okay. So here's the projectile diagram. Notice that I have Vx initial with some theta initial, some initial angle as an example, right? And then I have, vector, the velocity across the y-axis initial. So we have these two lines. And what happens over time is that the vector changes direction, right, for the motion, right? And the reason why it changed direction is because of that pesky acceleration, downward acceleration, which is known as gravity, right? So as the downward motion fights against the upward motion, it comes to an equilibrium, if you will, or a peak where the upward velocity has been canceled out by the downward acceleration. At this point, right, we have no upward, there's no y-axis component, and that's why you can see that the x component now has changed direction, so it's pointing towards the right, because the y-axis is less. Remember, the way to make this vector is we take those two components and we add them together to give us the direction, right? So there is no y, so it's going to the right, but now the y is starting to be more negative because the initial velocity that we had that was projected upwards, now it's been, it's translated now into accelerations on the downward kind of direction. And now you can see that the vector, the resultant vector now is downward, and it keeps going down, down, down until it hits the ground. And when the projectile hits the ground, we can say that the velocity ends up being 0. So there's 2 points in time where the velocity is 0. It's here and here, right? This is where it start off at 0, and then we have an initial velocity, the vector that carries us with magnitude to the initial point. So 2 parts where it kind of crosses the x-axis, 1 part where it crosses the y-axis. If left long enough, this is still going to keep going down, and if, let's say, for example, I was on the top of a mountain and there was no line here, this is not the ground plane, but this is kind of the initial plane where I was launching a projectile. It would pass below the initial plane of attack, if you will, and keep going down, 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 and it would almost form a straight line down eventually, given enough time and distance. Just look like it's coming straight down, right? But really it's following this parabolic path. And you can see that gravity is always pointing down, the gravity vector. So let's think about there's going to be several different types of motion that we're going to have to deal with. So here is the first type of projectile motion. Okay, the first type is exactly what I just said. If we have an object which comes off of a cliff horizontally, and it's eventually, and this is what's going to happen. It's going to come off the cliff, it's going to start up here, it's going to go whoop, boom, and it's going to hit the ground. Okay, so how does this work? In order to find the cliff height, then you can decompose, and here's equation number 1, and here's equation number 2. You can decompose the y component to say something like v initial t, right, plus 1/2 at squared. That is going to be your change in y, right? So that's how you're going to do it. And then the change in x is where you're going to say you don't care about the y anymore. You're going to say that you're going to take the change in x is equal to v initial across the x-axis. This should actually say v initial across the y-axis. That's what it should say, VIY. This should say v initial across the x-axis, v initial x, right, times time, right? And then notice that there is no acceleration component because gravity only works on the y-axis, not on the x-axis. And these two equations are kind of fundamental to building other equations going forward. Okay, so again, we would decouple these two equations as an example from the initial velocity. We'd be given an initial velocity, and notice that it just kind of falls down. So that is the first type of projectile motion. This is also a little bit misleading. I also want you to think about this as like it's pushed with no angle upwards. So there's no angle upwards. It's like literally pushed to at the horizontal. So straight with the horizontal, there's no angle. and it's going to fall kind of down this way. So there's no velocity, let's say in this case, the way it looks here across the y-axis. Okay, but remember, velocity is a vector, so the velocity across the y-axis could very well be a different kind of angle. All right, so we know that the acceleration on the x-axis is 0, so these things that we know. We also know that the acceleration on the y-axis is negative 9.8 meters per second squared, right? So therefore, we can derive this other equation where we can say that the final velocity is equal to the initial velocity, whatever that was, across the y-axis, plus at. That's where we can derive from, because we know there's no acceleration across the x-axis. At the top of the acceleration, so Vyi at the top is always 0, right? So again, the velocity with respect to y initial, as an example, starts off at 0, so therefore we can derive this. Remember I talked about this, that there is no positive y velocity going up. It's just we shoot across, on the x-axis. Okay, so we can say then that the velocity is equal to the total velocity is equal to the square root of the velocity across the x-axis squared plus the velocity across the y-axis squared. Okay, again, we're deriving one thing from another thing. That's how we're getting to these equations. Okay, and so this is the scenario we're talking about. Notice that the cannon that's on top of the hill, we don't really calculate the height of the cannon. We don't sit there and go like, hey, what's the difference in the height from the muzzle of the cannon? I'm not going to give you questions like that. I want you to assume that wherever this cannon is at the top of the hill. Okay, that the projectile, the actual projectile itself, wherever it starts, is at the top of the hill, the top of the range, if you will. Okay, and notice the velocity across the x-axis here. It keeps marching along at the exact same speed, right? That doesn't change, 20, 20, 20, 20. So the velocity vector across the x-axis, in this case, continues to stay at the same length. However, even though the velocity across the y-axis starts at 0, right? The velocity here across the y-axis becomes negative 10 meters per second, and then negative 20, then negative 30, and then it increases in size. So the magnitude increases in size, which means that the direction of the total vector starts pointing down. So you see a parabolic motion for the particle. Okay, and you can see that here when we hit the final position, let's suppose, and this is just a hypothetical, that the final velocity on the y-axis is negative 50 meters per second, but whereas the final velocity for the x-axis is the same as the initial velocity. It doesn't change. Again, all things being equal, not accounting for any air resistance across the x-axis, it's negligible, and no air resistance across the y-axis. For us, it's also negligible, okay, which doesn't exist, in other words. Now, if I had a different shape, instead of my particle being here a cannonball, if we can imagine our particle was a different shape that spread out the energy that was being applied to it, let's say it had wings, right, then it could have air velocity or buoyancy, air buoyancy, if you will, in many ways, could take effect. It could make it so that the thing could fly and it wouldn't hit the ground so fast, right? It may even, shoot up, as an example. But we're not dealing with that. Okay, so an object in free fall will accelerate with a gravity of, and here's the gravity vector, where the gravity vector on the x-axis is 0, and the gravity vector on the y-axis is negative 9.8 meters per second. So that is a vector. We just don't have a component for the x-axis. The x-axis is always 0. Okay? So again, think about this. Consider a ball falling off a table. What should be the equations of motion, right? If a ball is falling off a table. Well, this is the first type of, of motion. So if we go back to the two equations that we're looking at, we see that the delta x, the change in x, so the range that we're talking about here, this range here is number 2, right? The range in x, right, or the change in x is v initial x times time. So that is, this formula here is what I would put on the left side. When we break down an equation, what I want to do is decompose it into different parts, right? So on the left, VIY times time. On the right, we would have the other equation that we would start off with, right? Which is Vy times time, right? So plus the half gt squared, right? Which basically is, and the reason why I'm saying gt is because acceleration is only downwards. There isn't any, nothing to do with acceleration going up. And we're going to say half gt, and half g would be negative 4.9 times time squared. And that is the equation for the total distance fallen across the same time frame. Okay, that's what we have to look at. So then, if we break it down, we could use something like this. Here's an example of this, and I've kind of breaking it down so you've seen the example. So here's an example question. A ball rolls off a table with a speed of 3.2 meters per second. This is the classic example. The table is 1.5 meters tall. Okay, so what we would do is we would draw the diagram. Draw the diagram, label it so that the height is 1.5 meters, right, as an example. And the initial speed, sometimes speed is a misnomer. We want to say velocity. The muzzle velocity, if you will, or the speed of the ball, the velocity of the ball, is 3.2 meters per second. Meters per second is distance over time, right? And so we can see that it's going in a particular direction. It's rolling off the table. That's what's happening here, right? The same motion, this first type of projectile motion, example number 2. So we know we can break down those two, formula. The first one here, and here's the second one. And by the way, what I would do is I would break it down. So like I said, V initial across the x-axis, and then V initial across the y-axis is what this should say. So just to make that adjustment to your formulas online. All right, that's important to note. So V initial across the x-axis, let's put in what we know, right? We know that V initial across the x-axis is 3.2 meters per second. That's where it comes from. So we plug that in, 3.2, right? And then what we want to do for this one is we don't know the time frame. We don't know how long we have to find out the distance. So we just plug in this for now and we stop here. We can't figure out time, and we can't solve for time because we can't just put time on the other side and say 3.2. No. That's just the distance over time. We just don't know the time element right here at this point. So, but here on the vertical side, we can figure out how long it takes for the ball to hit the ground because we have some finite numbers. We know, as an example, that the distance from the bottom of the table to the top of the table is 1.5 meters. Everything is in meters, by the way. You should convert things to meters when you do these formula, right? So the total distance traveled is 1.5, but in the downward direction, because you're starting at an origin and you're going to the negative with respect to y, down, it's falling down negatively, right? So therefore, although we've been given that the table is 1.5 meters, it's going to end up from a negative displacement away from the origin. That's why we put in negative 1.5. So that's the total distance. The total distance across the y-axis. That's what this is, delta y, or the change in y over time, right? So we start off with the initial Vy initial. We know what we always been given is that on the y-axis in this scenario, that the initial velocity across the y-axis is 0, okay? And we know we're going to plug in just gravity and, divided by 2. Gravity 9.8 divided by 2 is 4.9. We know gravity is also, the acceleration due to gravity is also in the negative direction. So we're going to plug in a negative number here. So the new formula becomes negative 1.5 is equal to negative 4.9 t squared. And when we do some simple algebra and we divide both sides by 4.9, we get that t squared is equal to 0.3061, right? And what we want to do is we want to take, for us to find out t, then, what this should read, let's just plug in t. T then is the square root of, and by the way, when it comes to equations and symbols, PowerPoint and Word have the equations and the symbols here. So I can just say, okay, I want to plug in kind of an equation, as an example, a symbol. I can use a symbol or an equation here, right? So if it's an equation, right, like so, then what you want to do when you insert a symbol, again, you can see that there is a bunch of things you can choose. There's a lot of formulas that it comes with right away, right? The other thing that you can do when you inject an equation, right? And again, we want to modify this equation, right? I want to think about putting a square root sign here. So the square root symbol is what I could put in here. So if I looked at the square root symbol, and again, this is just the way we would describe it. So maybe I want to look at symbols, if there's something like that, right? And we could probably find, this is one way of doing it, the square root symbol in here if you really wanted to, okay? But what if, instead of doing the square root symbol, what's another way to do this? How do I create an equation? Because you're going to have to do this for your document. Ethan says, is the mass in Simon 1 just a red herring? In other words, is it required? Well, I want you to think about that. Is it? Does mass matter? Did I even have mass anywhere in here whatsoever? You know, the answer is probably not, right? So here's the equation. So again, let's undo that change. And a lot of times what we want to do for the new equation is I want to put it inside of some kind of text area. And the text area, what I can do is I can insert an equation inside there. So I can say insert a new equation, right? Here it is. And I can start typing the equation here, right? So I can start typing like, 0.361 is equal to t. But what if I wanted to make special symbols or something like that? So this is where I'm just showing you how I can make that equation happen, right? Let's do that again. So again, first thing is text box. Make a text box so that you can put the equation in there. And the next thing you want to do is when you insert the equation is you look all the way down where it says insert new equation. And now it's going to give you the equation dialog, right? This is kind of an important thing where you can see equation on the right-hand side, right? So again, what you want to do is start typing. So I want the square root. So you can see that there's a square root symbol, right? There's a square root sign. And then I start typing the square root of 0.361, right? And usually what I want to do is when I do this, I say the square root of 0.361, and I press space bar is equal to t. So that is what we want now from t squared. Square root of 0.361. Why? Or sorry, 0.3061 would be nice. I actually did it properly. There we go. Thank you. So then I can replace this thing. I wanted to show you this because, and I left it like this for you guys so you can see how this looks. Now notice that I have t on the right and I have my equation on the left. And typically what we want to do here, t is in time steps or seconds. And I want to swap this area around so t becomes on this side and this the result of the square root of 0.3061 goes on the right side, which is 0.5533 seconds, this number here. So now that we have total time that it takes for this to fall, well, we know there can't be any motion across the x-axis beyond 0.5533 seconds. We just can't be. It's going to fall. And once it falls, motion stops. We're assuming that there's no bounce, that there's no, so it doesn't bounce or slide, just falls and stops. That's our assumption here. Okay, that's important to note too. So we take this value for t and we sub it back into the value for the t value here on the x-axis. So we know that's the farthest it's going to go. So now we've solved for both the time value, this is the time value, as well as an example for the total distance across the x-axis. So again, here are the questions that we have to find. When does the ball hit the ground? Well, the ball hits the ground in 0.5533 seconds. How far away from the edge of the table is the ball when it reaches the ground? That's the displacement across the x-axis, right? Is what that works out to be, okay? And with what speed does the ball hit the floor? Well, we know that we can use V final is equal to V initial plus AT, right? Where V initial is equal to 0, and again, I can just put these Maybe I'll just put them down further so you can see this is the next part of the equation. We're figuring things out one step at a time, right? So this is the equation that I used to figure out question number 3. So if this is question number 1, so let's put in Q1. When does the ball hit the ground, right? So when does the ball hit the ground? This is around Q1, okay? How far does the ball hit the ground, right? As an example, then that is this one here, 1.771 meters, because it's the distance away from the table. And Q3 would be, as an example, with what speed does the ball hit the ground? Well, here we're using this equation, V final is equal to V initial plus AT as an example. And we got to think about this as VY final, right, is equal to VY initial, or VI, yeah, like this. It's written like this. It can be written like this. All right, or VY final. It really depends on how you see it. It's written in different places in different books, right? But you might see it VY initial. That makes more sense in many ways than seeing it like this. But you can also say V initial across the y-axis, V initial across the x-axis. Both mean the same thing. You don't see an option to download the PDF from the school Microsoft 365 PowerPoint. Can we just share it with you and leave it a link in the submission? Yeah, let me talk about that later, Neil. We'll explain how that works. All right, so then what we can do is we can sub in the numbers, and we know that A is negative 9.8, and the total time is 0.55333 seconds. We plug those two things, and we know then that the velocity final across the y-axis is a negative 5.4223 meters per second squared. What about the units? How many units am I going to require from you every single time? And my answer to you is, whenever you do units for me for assignments, always think about at least 3 decimal places, not 4, but 3. If I was going to ask you for units, okay, 3 is enough. If you wanted to do 4, you could, but no more. Please don't do more than 4 significant digits, because then that would be a little bit too much. You don't need to do that. Okay, so 3 or 4 is fine. All right, so that's the first one. So is everyone clear on how we got that? So again, we took information we know, right? This is part of our solution structure, right? We took the information we know, we drew a diagram, we applied the information we know onto the diagram, and we took the information components and applied them to the equations, the breakdown for the first type of projectile motion, because we've been given those equations online. Okay. Let's get into the second type of projectile motion. The cannon is kicking, or you're on a flat ground, as an example, so some kind of horizontal plane, and you're kicking a ball, or you're firing a cannon up at an angle, okay, on the horizontal plane. Okay, so this is the second type of projectile motion. Things that are important for this type of motion are the kicking angle, theta, and the initial velocity, vi, and that initial velocity includes both the x component, velocity across the x-axis, and is also velocity across the y-axis. A lot of times we don't have those two things. We're usually given something like, the speed at which the cannonball leaves the cannon is 10 meters per second with an angle of 30 degrees, right? What's the total distance traveled? So those are the things we normally are given. And again, what I talked about before is this very important concept of decomposing or decoupling both the velocity across the x-axis and the velocity across the y-axis, as taking the initial velocity, whatever that is, the total velocity. So if I say something like my total velocity is 10 meters per second, but I'm given an angle, theta, then I pass the theta angle into the cosine function for x, and I take the theta angle and pass it into the sine function for with respect to y, and I get the decomposed value of x and y. Guys and girls and everyone else, this is right here a fundamental way of doing stuff in games. When I want to find the next pixel if I want to look in a particular direction, as an example, I'm going to decompose the velocity vector, and we've actually done this in class together in AI, right? When I decompose the velocity vector and I say, here's, kind of a number of pixels on the x-axis based on the initial velocity, and a number of pixels on the y-axis based on the initial velocity, and we kind of feed it into the cosine function or the sine function. Remember that the angle that we get, if we get it in degrees, we have to convert it to radians when it comes to the computer, right? That's an important consideration. Not so if we're given an angle in degrees, we can use our calculators to figure out the cosine, using the degree method. We can also convert our calculators to a radians unit, where we can pass in radians instead. It's up to you. All right, so here's some important, some important equations. So equation number 8, velocity y final is equal to velocity y initial. We just seen this, plus at. This is the first one. At the top of of the motion, because again, we're thinking about it being parabolic motion. Parabolic motion means there's a B, almost like a height or an apex, if you will, of where the projectile is going to the highest point, if you will, of the parabola, right? And that's what we're talking about in terms of height. When at the top velocity, the top of the motion, velocity on the y-axis is 0 because it's not going up anymore. It's been canceled out by the acceleration that's happening across the y-axis due to gravity. So manipulating some of this initial equation, right, as an example, then we can decompose velocity across the y-axis initial, right, where we have an initial kicking angle. We can say that the velocity final, right, as an example, is 0. The velocity initial is v sine theta, right? Trying to find, again, the velocity final being like when the velocity final across the y-axis, when it becomes 0, is at the top of the parabola, right? And then plus gt. When we manipulate this, we can say that the total time it takes for us to reach the apex is v sine theta over g. Okay? That's for half of the motion. So that goes from this point here, A, to B. From A to B, the total time is, like it says here, v sine theta over g. Okay? But from A to C, which is from here to here, the total time frame is 2 times that, right? So just take 2, multiply by v sine theta over g, and you get the total time it takes for the projectile to travel from the initial point to the final point. Okay? It doesn't tell us anything about the height right now. All it tells us is, it just tells us how long it takes to get there. But with that number, with time t, we can plug that time frame, whether we're doing only to the top or the whole motion, we can plug those 2 time values into another equation to get the total height and so on. And we're going to show you that right now. So how can we find the maximum height between A and B? If we don't have time, we're not given time at all, or we don't care about time, we can say, well, v squared y final is equal to v squared y initial plus 2ay, so 2 times a across the y-axis acceleration, times dy. And then when we manipulate this, right, where we say that the height is a value of y, as an example, we can say that when the total height, then, if we manipulate the equation, is equal to v squared sine theta squared all over 2g. That's kind of the equation we've derived. Okay, and we also know that vy, as an example, the final vy at the top is 0, right? That's why we can sub in 0 here. Vy final, which is at the top. When we want to figure this out, when we know that this is 0, we can just massage the equation using algebra to get to this. Okay, so this is the height formula. We know what the maximum height is going to be given this information. Again, the initial velocity times the sine of the angle, theta squared, and then all over 2 times gravity, whatever that is. Okay. So let's go into, keep going with the second type. The other thing we also want to do is the displacement, or the horizontal distance, usually represented by R, right? Sometimes also represented by S, depending on the book that you're looking at. So if R is the range or the displacement away from the origin, and then we can see that R then is simply Vxt, where t is the total time for the motion, right? So again, we can plug in the total time given our calculations here, where we say the total time for the motion is 2v sine theta over g, right? So once we have this value, we can plug it back into this, and once we know the velocity across the x-axis, as an example, then we know the total time. Breaking this down further, we can say that velocity across the x-axis really can be represented as the initial velocity, the total velocity, times cos theta times time, right? So this is another representation of the same formula. It's just a derivation, if you will, right? And once we have that, if we weren't given time, let's say, for example, we don't know the time, we haven't been given time, but we've been given other information, as an example. We've been given the angle, we've been given the velocity, and we want to find the total range, but we've never been given time. We don't know what the time is. We don't need the time because we know that gravity is something that's going to be in play all the time, no pun intended. We can rework the velocity vector in that we can plug in some of the formulas that we already know, right? And we can massage the range vector to end up looking like this, v squared sine 2 theta over g. Okay, and that's the range, the total range function, given the information we have. And this is also using a trigonometric identity, which you don't need to know. Okay, so that's the other equation number 12 is this one, right here. All right, so again, really super important because we took the total time. We know the total time goes 2v sine theta over g, and all they're doing is they're replacing, we're actually multiplying that only across the x-axis, right? Because this whole thing represents time. This whole thing is the total time, right? And we've taken our initial equation, which is v cos theta times time, and so we sub out t and we replace it with this information here, and that's how we come to this point for those people who care. Okay, and once we have here, we use some manipulation with trig and algebra, and we get to this point. All right, so that is the second motion. Second motion is parabolic motion. Third motion is more complicated. All right, it's like the hill example, but it's actually the most complicated type of motion because we actually have upward thrust. We have both angle for velocity. Velocity zero does not start off, or velocity initial does not start off at zero for the y-axis. It's something else. It's not a straight line motion for this at all. It's like I'm kicking a ball off the top of a cliff at an angle, or I have a cannon and I'm aiming it up, as an example, up a cliff as an example, or kind of higher up, right? So when we're thinking about the total time it takes for the ball to hit the ground from A to C, right? The graph is not symmetrical, right? Why? Because there is a motion like this, and again, if this is not a great, graphic, but the way to think about it is the motion that we're going to describe. Let's see if I can actually do this. I probably won't be able to do it any more justice than this, but again, you've got your cliff face. So let's suppose you have your cliff face, and then the initial kicking angle is this way. So your parabolic motion goes up, and then slowly over time comes down. Right? Well, what's happening is when you do that, there is a plane which seems to be that there's like two problems here, right? The first problem is motion type 2. This problem right here. So this is motion type 2, right? And this from here, let's suppose this was the top of the cliff now. This is like motion type 1, right? So this is type 1 motion. So it's almost like we're combining type 2 motion with type 1 motion to get the total motion that's happening here in type 3. And so type 3 is like I got a kicking angle and I'm falling down. So what's happening is there's a symmetrical motion from here to here, right? And when it gets to this point right here, then it becomes just the second type of motion, okay? However, there's some changes that happen here that aren't exactly like the first type of motion, which we're going to talk about that in a second. So, what do I mean by this? Well, you can use another type of formula where we know that y final, okay, again, we can break it down into two pieces, right? So from A to C. Here the graph is not symmetric, so the time between A and B is not equal to B to C, right? So we can use two different ways to get this answer. So the first way is using, assuming that y final is equal to 0. So the final velocity, the final, y is going to be 0, right? Or the position, final position is going to be 0. So assuming this, then what we can say is y final minus y initial, right, is this piece. We're kind of subbing that in for the total distance traveled, right? And we can say that we can still keep the same equation because this equation here, my friends, is the exact same equation, which is p final is equal to p initial plus v initial t plus 1/2 at squared, that whole parabolic motion, right? But we know distance final is 0. Okay, when I say 0, it means it hits the ground. If we assume that this is 0, okay. So once we massage, the equation, we get to this equation right here, which is what I just said. Okay, so this is the new equation. Knowing this, then we can say that we can sub in some values where we can say that 0 is then equal to the height, the total height that we're talking about, plus v sine theta t plus 1/2 gt squared. That's the new equation that we're going to use. And we need to use the quadratic formula for time because we're using 3 terms here that's in quadratic form, right? So we have a squared term, we have a scalar term, and we have an additional term, right? This is taking the form of ax squared plus bx plus c, like we've shown before, and then we can take these values and sub them into the quadratic formula for t, where we get 2 possible values, but we only care about the value of t that is positive, not the value of t that might be negative. We can now calculate the time it takes for it to fall. And once we find the time that it takes for it to fall, then it's simply, we can start trying to figure out how long it takes for certain things to happen. So the second way to find this is actually to, how long it takes for the object to hit the ground, is to separate this problem into 2 pieces, okay? And that's the second way of doing it. So we can say from the time it takes from A to B is v sine theta over g, just like we saw in the second type of motion. Remember, second type of motion way up here, and we talked about how long it takes for us to get to here, right? And that was over here. This is the initial thing. We say that from here to here, how long does it take? We're going to say that it's not the first part of the motion, which is not symmetrical, is v sine theta over g. So we start with that. Okay, we start with this point. And if we go back, which is the second form, we take that initial formula. So from time from A to B is time from A to B, this part right here, A to B. Okay, and that's how long it takes to get there. We also know that the height is v squared sine theta squared over 2g. We know that as well. And so then the total y is 1/2 of at squared. So the total height from B to C is big H, which is this one right here, this height here in this parabola, which we can figure out from the motion type 2, and the total height of the hill, which is how high up you are from the ground, from the 0 point, if you will, right? We add those two together, and that's the total height. And once we figure out the total height, then we can plug that into something called y max, so the total maximum height, right? So now we know from the time between B to C is the square root of 2y over g, where y is y max, the total height that we're adding together, right? And then with some careful manipulation, we can say that time A to C is equal time A to B plus time of B to C. Make sense? The time it takes for one part of the motion to the time it takes for the second part of the motion, we add those two things together and we get the total time for the entire motion. And the time is really special. It's really important because once we know that, then we can calculate the distance. We can do a bunch of stuff once we have the total time. Time is the key when it comes to a lot of this stuff. So to find the range then, we can say that the range, just like before, is Vxt. Once we have the time, we just plug in, that's the range. The total time we calculated just now, which we can derive from those two components of those two portions of the problem, right? We add them together, we get that time. And then we can use that for Vx, the velocity across the x-axis. Of course, we can break the velocity over the x-axis over, especially if we've been given an angle, only the angle. We've normally not given this value. So we can take the total velocity times cos of the angle, the kicking angle, times time. And then we can figure out how far it goes across the range from the base of the hill, if you will. And again, once we, the last two formulas, we can find the time, and to find the speed of the ball before hitting the ground, we know that velocity across the x-axis is always constant, just like we saw in the initial cannon, where the velocity vector keeps constant, but then what's happening is the acceleration across the y-axis, the velocity across the y-axis, which is influenced by gravity, continues to increase, right? We can say that the velocity final, right, across the y-axis is equal to v sine theta, right? This is the velocity component across the y-axis plus gt. Okay, and with some careful manipulation, we can figure out a couple things. The final velocity, which is again using the same equation. We're just bringing the same equations back in, and we can also find theta by taking the arctangent and taking velocity across the y-axis and dividing it by velocity across the x-axis, this ratio or gradient, and we can pass it into the arctangent function to get the initial kicking angle, if we're going to find that out. So lots of stuff we can figure out with the information we've already have. One thing to note is when we ever plug in the values for velocity across the x-axis and velocity across the y-axis, make sure these values are positive for this type of motion. Okay? Because we're deriving stuff, and sometimes if you make the y negative, you'll get the wrong answer. And the y might look negative, but you got to consider what's happening in this type of motion, which is asymmetrical. So the vertical velocity is always 0 at the top. That's one thing to note. And one thing also to note is the acceleration is not 0 anywhere along the trajectory across the y-axis. So we continually have constant acceleration the entire path. Why? Because gravity is constant. Okay, we can assume gravity is a constant then. So again, we can consider the motion, this total motion, and what they call it as the superposition of the motions in both the x and y direction. So we actually compose them together. We use composition to compose them together to get that total direction, or the total motion of movement. Which notice what this is again. Final position or final range is equal to the initial range plus the initial velocity times time plus 1/2 gt squared. We've seen this over and over again. It's parabolic motion that we're talking about here. Okay, and the initial velocity can also be expressed in terms of its components, where Vxi is equal to Vi cos theta, so Vi being V initial, and Vyi is V initial sine theta, right? We've talked about this before as well, right? Acceleration, these are all knowns. Acceleration across the x-axis 0, a summary, and acceleration across the y-axis is always negative g. Okay, we kind of covered this and, kind of the same thing. It just goes into more theory about the height And when the height is maxed, usually the velocity is 0 across the y-axis because it's been canceled out by the acceleration across due to gravity. And then here is the height of a projectile equation that we've seen before. Okay, and the range. So this is just decomposed for you to look at aside for the motion. Here's one important aspect of angles. There are, we're going to say, complementary values for these angles. An example would be if I kick off an angle at 75 degrees, so the same with the same velocity, whatever that velocity might be. Let's say, for example, 10 meters per second, right? And here the velocity is 50 meters per second. If I'm using the velocity, the same initial velocity, 50 meters per second, at an angle of 75 degrees, you can see that the object will come up and then come down somewhere around 125 meters away from the origin, okay? So too, though, is if the angle was around 15 degrees. Take a look at that, 15 degrees. So that'd be a very shallow angle of attack. Question for you, is the time the same? Is the time the same from 15 degrees to 75 degrees? Patrick says no. And Patrick, that's very astute. It makes sense. Same thing with Samuel. The reason why you guys can see it's intuitive, it takes more time, is because look, now we're talking distance. Total distance traveled for the projectile is longer across the 75 degree angle mark compared to 15 degrees, right? The distance is the same. The displacement from the origin is the same, right? This is faster. So if I angle something lower, it's going to hit the same place, the same position in much less time than if I shot it up into the air at 75 degrees. This is the complementary angle. Here's 60 degrees. So I've got 60 degrees or 30 degrees. Those are complements again. So if I go up 60 degrees, you can see that I end up down over here. But so too, if I go 30 degrees, I end up right over here, the same position. They're complementary angles. And by the way, look at the relationship. 75 and 15 add up to 90 degrees. 60 and 30 add up to 90 degrees. And again, 30 degree angle would obviously be faster than the 60 degree angle. But there's different utilities for these angles. Example, I want to fire a projectile over a wall. Should I go, there's two possible solutions, right? To get to the same, kind of location. So let's suppose I'm going to draw a wall here. So let's suppose I have a wall that is here, right? So I draw a wall here and at some height, let's say 110 meters, right? So the question might be something like, I want to hit a target on the other side of the wall, let's say at about 125 meters, when I, with a muzzle velocity, if I have my cannon that shoots a projectile with a muzzle velocity of 50 meters per second, what is the solution angle, right, that I need to use in order for me to get the projectile over the wall, right? And so we can figure out the total height. The height here is much greater than the total height here. And you can map out the projectile motion to know that although it takes longer, right, with the same velocity, it's going to end up at the same location as an example we would if we fire through. But here it would be blocked because of this wall, whereas in this solution, this angle, it would just work. If ever you're asked in a question, what is the farthest an option or an object can fire, or the farthest distance an object or a projectile can travel with the best angle to fire, it's 45 degrees. 45 degrees is the best angle because it's going to fire the farthest, not including any kind of obstacles due to height. So if I didn't care about height and I just want to fire an object, any projectile, the farthest distances I'm going to shoot at a 45 degree angle relative to the horizontal plane. Why? It's going to keep traveling much farther. There is no complement 45 because 45 plus 45 is equal to 90, so it's the same angle. 45 degrees is the key, right? Now, it doesn't mean that if I had something like this and I said, well, I want it, I have an obstacle and choose the, the firing angle, whatever it's going to be, right? That's great. But what about if I could modify my velocity? If I had a trigger on my velocity, how far I can go? If I want to hit the same location that I would hit at 45 degrees without an obstacle, so I'm given a distance, let's say, for example, 260 meters, right? I'm just coming up with this. If I have to hit a distance of 260 meters and I have an obstacle that is 125 meters high at this particular distance away, this could be the kind of question you might get in a more complicated exam. I'm not going to give you this type of question, but you might get this. What would be the optimal velocity? I might ask you for the optimal velocity and the optimal angle that you need to trigger it in order for you to avoid hitting the wall and attaining the distance that I need. Is there a solution? Is the question I might ask you. And there normally is. If I can vary my velocity, right, unlimited, if I can go any type of velocity I want for my muzzle velocity, that's great. But if I give you a range of velocities, the minimum velocity would be 10 meters per second, and the maximum velocity might be 70 meters per second, as an example. Is it enough, given that range of velocities, can I, shoot an option or trigger an obstacle to fire over the obstacle that's here in front of us and land at this particular point in time, this exact location, right? Really challenging. All right, so yeah. Good graph. All right, so again, the range of a projectile, we know that, like I said, that the theta initial, if you want to find the maximum range, it's 45 degrees. Complementary angles have different heights and different times. Okay, that's kind of an important feature of this thing altogether. All right, so whenever we do, here's some hints now on problem solving, because you're going to be given some problems to solve, and even the Wookiee problem as an example that you've been given for assignment number 1, right? So I want you to think about this now as an example. You're going to conceptualize. You're going to try and take the information you've been given and plug it in and start analyzing what type of formula you can use. What type of motion is this, is what you're going to try and figure out. And then once you've done that, once you plug in your numbers, finalizing is just finding the solution for your formulas. Okay, here's the first problem, okay, that we have. The first problem. This is a non-symmetric projectile motion problem. This is what type? What type of motion do we have here that we're describing? Type 3. Yay, third type, right? So we know that it's not the regular type because we have a theta value. It's not motion type 1. If it was motion type 1 off the top of a building or a cliff, it'd be straight where V initial is 0. All right? Vy initial will be 0. Here we don't have that. We have, Vy or V initial is equal to 20 meters per second, and we're given a kicking angle of 30 degrees, okay, away from the horizontal plane at the top of the building. Notice that the top of the building in this case is also including the kicker, which is this guy right here. So it's at his head, or the place where he's launching the projectile. All right, that's considered the top. Again, so again, what we want to do is break the y direction down into different parts, right? So we're given the formula where Vx is equal to V cos theta. We know this, right? So we want to get that broken down. And let's sub in what we know. V, which is 20 meters per second, and then 0.866, right, is what works out, what we get back from plugging in 30 degrees into the cosine function. So 20 times 0.866. By the way, 0.866 is a very common response from cosine of 30 degrees. You're going to see other kind of repeating numbers. You're going to see them over and over again. All right. And then our final Vx, so velocity across the x-axis, is 17.3205. And then we should put in there what? Meters per second, which is something that's missing. So 17 meters per second, roughly, is the total energy. This is another way to think about this, right? if I have energy, let's just say 20 units of speed. Okay, it doesn't matter what it is, 20 units of speed. Not all of the units of speed can be used across the x-axis because of that kicking angle. Some of that energy is being absorbed into the y-axis, right? How do I know this? Well, if I take v sine theta, so if I plug in 30 degrees into sine, what do I get? So let's bring up my calculator again. And if I bring, kind of 30, and then I put it into a trig function like sine, it becomes 0.5. So 30, sine 30 is always 0.5. So 0.5, meaning that I take 20, multiply it by 0.5, and I get 10 meters per second. So that is my decomposed values, right? And again, let's just use just an extra a bit of information here. First thing that I want to do, break it down so I know, the values. So v, which is 20, and then times sine theta, which is 0.5. So that's what I want to put in here, just so that way we can be the same. Okay, sine theta, which is 0.5. Okay, we can actually have another step in here if you really want to, where you say v sine and 30 degrees. So 20 sine 30, that's okay too. All right, but this is kind of what we're showing here. We're showing that we have these two breakdowns of components, these two components. Okay. So once I have Vx and Vy, there's a lot I can do with it, right? This is the first piece that I need, Vx and Vy. Once I have these, then I have decomposed the, the velocity across both the x-axis and the y-axis. Part two, once I have this piece, right? How long does it take for the particle to hit the ground? That's the next question I want to answer, right? How long does that happen? Well, okay, if this is 45 meters and I've got my two pieces there, then I know that I'm going to use my symmetrical motion, that I'm going to plug in, and this is a type 3 problem, right, as an example. So I have some information about this right down here, right? I have information, right? So where I have 0, which is the formula that I'm using, is equal to the height. So there's two heights, right? There's the big height, the height of the building, as an example, plus the secondary height, which is this height right here. Okay, so that is something that I want to think about. So minus 45, I put that in there as 45 degrees because I'm falling downwards, and I multiply that by v sine theta t. We know that sine theta t, v sine theta t is 10. We've already figured that out, 10 meters per second, right? And then we plug in what we know, which is negative 4.9 for gravity, right? And then what we do is we use the quadratic formula, this formula right here, and we solve for t. We plug in the values of t into this formula here, and we have two values of t. We're going to get two values of t because this is plus or minus, which means we can get a positive value and we can get a negative value. One of the values that we're going to get is a positive time value. Sometimes we get two positive time values, and then you got to look at it and go, does it make sense, right? So that's the things we're going to get. But most often you get a negative value and a positive value. We're not time travelers, so we ignore the negative time value and keep the positive time value, which is typically the solution. And we take that time value and we multiply it by v cos theta, which we were given as 17.3205 meters per second, multiplied by the time value that we found from here. And now we know the total range from the bottom of the building that this thing would fall. So that's kind of a way of doing it. Okay, any questions around this? Again, when it comes to problem solving, I want you to think about, how do I break it down? How do I draw the problem out, I sub in the information that I know, and then I try and derive some of that, the answers for this thing. By the way, there's a lot of stuff online. The minus b formula again. How do I get that? Okay, so he's asking, how do I use the quadratic formula? So this is the quadratic equation, right? So I'm just label it for you guys so you remember. So this is quadratic equation, right? Or the quadratic formula, if you will. So the quadratic equation, what it does is it says, typically what I have for the quadratic equation, and the way to figure this out is we start off with another formula altogether. So let me just put in another line in here. This is just, I want to help. So you asked me to help, I'm helping, right? So I know for some of you know this already. So please bear with me as I'm trying to make sure that I have everything in place. So what I want to say is, then I want to solve for t. T is really like me solving for x, right? And we have the quadratic formula, right? That we normally get, which is a. We start off with the term a, which is a scalar, right? Not a as in acceleration, but just a, the first scalar that we're going to use, multiplied by, I'm just going to use this value here, x squared. So ax squared, right? This is the pattern or the form, the general form that the quadratic formula takes. Ax squared, right, plus bx plus c. Okay, so that's the general form of the equation that we normally get, right? So ax squared plus bx plus c, solving for x. This is, instead of solving for t, I'd be solving for x, right? I want to solve for x, right? How do why do I need to use this equation to solve for x? Because of this, because of the squared term. The squared term provides two separate solutions. So we're going to say there's one solution that has a positive. We say minus b positive. We do figure that one out first. And then we do the same equation again, and we just, instead of adding this piece, we subtract it. Then we're going to get two possible values. Why? Because it's a parabola. The parabola hits the x-axis at two different time frames, right? And so because it hits the x-axis at two different time frames, we're going to get two solutions. A lot of times, in our case, one that's positive and one that's negative, right? But what's happening here, this isn't x for us, it's t. So if I sub in t for x, where time is x, let me just rewrite this equation for you, right? So who cares if it's x or t? It's just a variable for us programmers. We don't care. We can sub out t, and then we can rewrite it into the form that we know. By the way, it's usually this is equal to 0, okay? We can rewrite it so in the form that we see, which is something like, I want to solve for t, so I want to say, if I rewrite it, right, then I can say that the final position is equal to, this is some kind of parabolic motion that we're having, right? Where this is p final, or whatever it's going to be, right? So if we're given this value, the final position, it can help us derive t, because we can kind of do substitution here for c. C can be put over on this side, and we can get some kind of values. But really what happens is, this is just rewritten down here. Look, this is the same equation, but just rewritten in a different order. So it's written like this: 0 is equal to, right? Oops. 0 is equal to, c plus bt plus at squared. That's really how it's written for us. That's the form, right? That we normally get in physics. We get this form. But who cares the form that we're getting? And even if it's 1/2 at squared, because a lot of times we're given this 1/2 at squared. Who cares if it's 1/2? It's still a. It's still that first term. The first term has a scalar that is a. Whether it's half gravity or all gravity, it doesn't matter, right? So then all I have to do is sub out. So a then is this piece, 1/2 of g. That's what a is. And b is v sine theta. That is b. And c is the height, right? That's right here. And then when we sub those things in, we get these values, right? And we take these values and sub it into the quadratic equation, or the quadratic formula, and then we solve for t, and we get those two values. Okay, that's how it works. I've just rewritten this so they can see it in the same form of our parabolic function. Okay, hopefully that makes sense. All right, let's continue with this. So we're also going to talk about circular motion. Now, one thing that I'm going to tell you is I'm not going to make you crazy with circular motion in this course. I'm going to try and keep as linear as possible when it comes to what we're talking about, because when it comes to circular motion, it can be very challenging, especially when you do things like circular collisions and those things. Motion due to collision due to some kind of circular motion or angular momentum or something like that. But one thing we need to know is what happens when with circular motion. How does the velocity work with circular motion? And we know that the change in the velocity is due to the change in the direction. Okay, so imagine that we have some kind of tether and that we're kind of rotating something around a center, right? Then the velocity would kind of be changing directions every single time, where velocity initial is equal to velocity final. Notice that these two ranges are the same range. Okay, the angle is kind of how far you move from A to B, the angle that you're changing, right? But really, if you think about this, it's all related to the same things we've learned before, which is velocity final is equal to velocity initial plus some kind of delta V, right? Where delta V is the change in velocity, okay? So that's the thing, that's where it comes from, this idea of trying to figure out circular motion. So we're going to talk about two things. There's one thing called centripetal acceleration. And this is the acceleration that is always perpendicular to the path of motion. And the acceleration always points towards the center of the circle. So if I have centripetal acceleration, right? Also, we're going to learn later on, there's something called centripetal force. It's going to point towards the center of the acceleration, right? And we can say that the centripetal acceleration, so AC, is equal to v squared over r. This is the formula that's been derived over time, right? I'm not going to go through it again and show you this thing, but where r is the radius and v squared is the velocity squared, v squared over r. Okay, we're going to see this formula again and again throughout the time that we're together. Period, if we're going to find the period, and period is the time required for one complete revolution around, if I'm swinging a pendulum or something around, let's say I have some kind of sling and I'm, swinging the sling around, how long does it take me based on the speed that I'm swinging it around, right? For me to complete one revolution of my swing, as an example. Well, we can figure out that the speed of the particle be the circumference of the circle of motion divided by the period. So we can say then that the period t is equal to 2 pi r, right, which is the circumference, over v, the velocity, how fast I'm swinging it. The faster I swing it, as an example, then the smaller the period, the smaller the time, right? The larger the denominator, the smaller the number that I'm going to get, right? So the faster I swing it, the faster, the shorter the time frame. That's what this means. There's also something that we're going to hear called tangential acceleration. And tangential acceleration, it's hard to say that 10 times fast, is the idea where we're going to get acceleration, tangent to the curve, right, of the angle of motion, if you will, right? And note, let's think about this as some kind of roller coaster, and we can see that the particle path is here, but as the particle might have an acceleration up here, it's going to follow this path, and the acceleration will change, the direction will change as you're moving around this circular path, right? Where we have two circles, one here, and we have one here, okay? So tangential acceleration causes the change in the speed of the particle. That's one thing. And there's also something called radial acceleration, which comes from the change in the direction of the velocity vector, okay? So those are two other terms we have to think about. So tangential acceleration can be thought of the absolute value of the change in velocity over the change in time, okay? And that's what the tangential acceleration is. Radial acceleration is usually the opposite of centripetal acceleration, where centripetal acceleration points towards the center of the rotation. Radial acceleration points outward, away from the center, right? So that is the exact opposite of centripetal acceleration. So it's negative v squared over r, okay? And then when we think about the total acceleration, that's something different, where what we want to do is we want to take the total tangential acceleration squared plus the total radial acceleration squared, and that's going to give us our total acceleration when we take the square root of those two values. Because we're both adding the radial acceleration, which goes away from the center, plus the tangential acceleration that goes tangent to the curve, right? So at right angles to the curve, right? And the tangential acceleration plus the radial acceleration, it looks like a triangle. And again, we're going to get the total acceleration, which is really Pythagorean theorem again. Okay. Sometimes also, and this is not relative to what we're talking about, but I want to talk about it because it kind of connects all the dots when it comes to our physics. We have something called relative velocity, right? And a lot of times we might hear of a term in physics called a frame of reference, okay? And one thing, it doesn't really apply to us when it comes to, games, but it's good. I put it in here for your reference. So think about, our frame of reference. When I'm on a slide walk, as an example, a person that's in the slide walk, from their frame of reference, they're not moving at all, right? Because they're just standing still, right? But from the frame of reference of the observer, that person is moving because of the slide walk. The system that they're on is moving. And so from the observer, the person who's outside of the system, they're seeing motion. But the person that's inside the system, their frame of reference, they see nothing, right? So a slide walk. Okay, and that's the idea of a frame of reference. We're not going to talk too much more about a frame of reference or relative velocity because it's outside the scope of what we're talking about. I'm just going to skip this stuff. And what I have at the bottom for you to finish this off is some examples I'd like you to take home for homework. Joss may cover some of this. I would ask him about this when you talk to him about some examples that I've given you for this day. Usually I give you some examples that you can practice, right, that are here for you to practice on your own. And I've given you enough examples so you can go through. So example, how would you figure this out? This is the last thing I'm going to talk about, guys, and I'll let you guys go. I know that you guys were at the end. So here's something. A water balloon is thrown horizontally, right, with the speed of v naught, so the initial velocity of 8.31 meters per second from the roof of a building with a height of 23 meters. How far does the balloon travel horizontally before striking the ground? What type of motion is this? What have we been given, and what type of motion is this, guys? Talking about projectile motion, 3 types of motion. Which one of these types is this? Type 1, type 2, or type 3? Which one? So let's draw it out. Catherine says type 1. A bunch of people say, some people say type 2 or type 3. Let's see what we've been given. Remember, for type 1, we don't have an angle. So type 2 and type 3, you guys, you're wrong. It's type 1. So let's start drawing it out. Let's draw out this thing. So if I'm going to draw it out, I draw out the building, right? So here's the building. And then I draw a height. So I start labeling, right? And this is kind of an important thing to do. I start labeling this thing. I say, well, the height is 23 meters, right? So I kind of put that into play for the building. So this is the building height, 23 meters, right? And then it says the water balloon is thrown horizontally. Again, we can try and draw this thing. Really, it's like doing something like this, where I want to draw something like this kind of motion, right? So the water balloon is thrown horizontally, and this is the kind of motion it's going to have, okay? So let's do the shape fill, no fill, right? So this is the motion we're going to have for the water balloon. We know that the initial velocity across the is 8.3 meters per second from the roof of the building, and it's the horizontal, thrown horizontally, which means across the x-axis, right? So again, if we're going to figure this out, then we know that the velocity horizontally, so Vx, right, is equal to 8.3 meters per second. Okay, we know these things, these facts. This is what we've been given, all right? And we know that the angle would be this way. This is the angle. So from here to there, that's the velocity. The initial velocity is, 8.3 meters per second. You start drawing it like this. This is what you would do, okay? So once you've got this happening, how far does the balloon travel horizontally before striking the ground? We want to know the range. That's what we're looking for. So the unknown is really this piece from here to here. This is the part we want, this part, okay? And so again, you break the problem down. So when you're doing your test, what is this? That is what the question is asking. What is this piece? How far is the range, right? And how do you figure that out? Well, you plug in the equations I've given you earlier. That's how. And you might break it down between the x component and the y component. Okay, so this is kind of a beginning for this one, right? I know I'm going long. Bear with me. All right, next question. An object is fired from the ground at 100 meters per second at an angle of 30 degrees to the horizontal. What kind of question is this? Type 1, type 2, or type 3? Which one? Is it type 1 motion, type 2 motion, or type 3 motion? Ethan says type 2, and people who say type 2 are correct. Why? We know it's fired from the ground, so the person that's firing it is not on a cliff, right? And we know we have a velocity initial, which has both x and y components. And we know that the angle is 30 degrees. Now we can figure out the rest. We draw it, how it looks, the parabolic motion. It's parabolic motion we're looking at. And it's asking us some questions. Calculate the horizontal and vertical components. It's the first thing we do. After 2 seconds, how far has the object traveled in the horizontal direction? That means across the x-axis. And how high is the object at this point? Give me the height at that particular point in time. We can use the formula from the type 2 type motion to figure this out. Next one. Mary throws the ball to the x direction, horizontal, with an initial velocity of 10 meters per second. The time elapses during the motion is 5 seconds. Calculate the height that an object is thrown and the Vy component of the velocity after it hits the ground. Again, what have we been given? We haven't been given an angle, right? We haven't been given an angle. But we know that we say Mary throws the ball in the x direction. Well, this is type 1 motion, right? With an initial velocity of 10 meters per second, right? So we haven't been given some other information, though. We know the time. The total elapsed time during the entire motion is 5 seconds. That's the total time. We've been given the time, but now we're looking for the height that the object is thrown. Okay, so that's what we're looking for. What's the height of the building, right, that we're throwing it off of? Sometimes they're weird worded questions like this. Adam kicks the ball, and the ball does projectile motion. I love this one. With an angle of 60 degrees to the horizontal. Okay, let's reword this one. Adam kicks the ball with an angle of 60 degrees to the horizontal, right? Its initial velocity is 10 meters per second. Find the maximum height it can reach, horizontal displacement, and total time required for this motion. Again, type 2, right? And the final one is, given an object on a cliff that gets fired, given the initial velocity of 10 meters per second and an angle of 30 degrees, the height of the cliff is 10 meters. How far does the object go along the x-axis range, as an example, in delta x? So it's really worded badly, but you should look at it and say type 3. Why? Object on a cliff with an angle. Object on a cliff with an angle, type 3 motion. Okay, it doesn't matter what it says. I can mix up the words and not say anything. I can just say these words: angle, cliff, motion, angle, cliff, angle. Angle, cliff with a velocity. I have a projectile fired at a velocity with an angle on a cliff, type 3. once I say that, right? And now I need to get some information. What's the height of the cliff? What's the angle? What's the speed what's my muzzle velocity? Those things are important for you to figure out the finals, right? So that's what I'm talking about there. So always start with a picture like this. And once you start with a picture, you can start figuring out, what the resolution is. So what I want you guys to do for your homework is go through these questions, because these questions are going to be eerily similar. Excuse me, eerily similar to what you're going to see on your test. Eerily similar, guys. Very, very similar to what you see in your test. So make sure you go through these things. I'm going to give you other questions like this as an example. And one thing that I'm going to also give you is a cheat sheet, a quick way of looking at, one pager basically that allows you to see all the formula there that I might use, and you can reference that formula in order for you to, or the sheet to be able to answer the questions. Okay, so that way it's not difficult for you. But it's really applying your knowledge to the problem and trying figuring out the problem. Yes, I'll give it to you later. So it won't be now, but I'll give it to you, kind of during your test. Okay. Questions around anything we talked about today? So we covered a couple things. We covered at the end. We covered centripetal, circular motion, and in the beginning we also covered motion in two directions. Those are the things we covered today. No formula memorizing. Nope. No. You can also find the answers, Samuel, online. There's a lot of stuff online if I want to plug in a formula or something like this, and you can plug in the formula and find it out yourself. The thing for you to figure out is, and you can ask Joss as well, say, does this look right to you? How does it look? It should make sense to you. And the thing to check is backtrack and check your work. Plug in the numbers again. But the first thing that I would do here is break it down with your components of motion, the x-axis and the y-axis. How can I decouple those two things? And what information do I need to plug in? How do I find time? Time is kind of a key to figuring out the distance a lot of times. Okay? All right, that's it. I'm going to stop the YouTube stuff now, and I will take any other questions relative to your assignment or anything else you have. Otherwise, that's it for me today, guys.